Before going any further into what this breakthrough could eventually mean for the wider AI industry, it's worth pulling back and understanding exactly why a project like this is emerging from China, specifically right now. According to analysis from the Center for Strategic and International Studies, the approach behind this breakthrough deliberately leans on mature, standard silicon fabrication processes rather than the leading-edge chip manufacturing technology that's currently restricted under U.S. export controls. One specific reason analysts have increasingly singled out silicon photonics, the broader technology category this optical chip belongs to, as an active front in the ongoing U.S.-China technology competition. Here's the thing that makes that strategic framing land differently once you sit with it. Rather than racing to match NVIDIA and other Western chip makers on raw manufacturing precision, a race made significantly harder by export restrictions, specifically targeting China's access to the most advanced lithography equipment. Chinese research institutions appear to be deliberately routing around that entire bottleneck, focusing engineering effort on smarter system architecture and interconnect design instead of chasing ever smaller transistors on ever more advanced fabrication nodes. This is not an isolated lab curiosity happening in a vacuum. According to reporting tracking this space, this Peking University result joins a broader run of Chinese optical computing announcements over the past year, several of them separately claiming large performance gains over NVIDIA's own hardware, suggesting a genuinely sustained national research push into optical and photonic computing as one specific pathway toward reducing dependence on the most export-controlled categories of chip manufacturing. And once you see this result as one entry inside that broader pattern, rather than a single isolated headline, the honest limitations of this specific demonstration become just as important to understand as the impressive parts. Here's the honest concession worth sitting with directly, because credibility matters far more than repeating an impressive multiplier without context. Independent reporting covering this broader wave of Chinese optical computing announcements has specifically stressed that these dramatic performance wins, so far, hold up only for narrowly shaped laboratory tasks, rather than the full, messy range of workloads a real commercial AI data center actually has to handle day to day. Here's exactly where that caveat applies to this specific study. The researchers' own published results acknowledge that this demonstration used only small 5x5 convolution kernels, a comparatively modest and simplified workload by the standards of the massive, sprawling AI models currently being trained and deployed commercially, meaning this test proved the underlying concept works, but it did not prove the system can handle the scale or complexity of a modern frontier AI model. Here's the other limitation the research team themselves flagged directly. Reaching the system's full intended 16-chip design, rather than the 5-chip version actually demonstrated, will require faster data input and output speeds on the FPGAs themselves, meaning the architecture's ability to scale up to its full stated potential remains a genuine engineering challenge still ahead of the team, not something already proven inside this specific published study. Think about what that combination of caveats actually means for how to read this breakthrough honestly. This is a real, independently verifiable proof of concept, with real published data backing up a genuinely extraordinary result. But it is not yet evidence that this exact system is ready to replace GPUs inside a live, commercial AI data center handling real-world traffic at scale. Here's why that honest limitation doesn't make this breakthrough any less significant, though, and here's what the researchers themselves say it's actually pointing toward. In their own words, published directly in the study, the team wrote that specific objectives can be realized under limited computational resources, when algorithms, processor microarchitectures, and chip-level interconnections are all deliberately co-designed together, rather than treating faster chips as the only lever worth pulling. Here's the broader implication buried inside that statement. The entire AI industry's current strategy for getting more performance has largely been build bigger, more powerful individual chips, and then build more data centers to house them, an approach that comes with enormous and rapidly growing energy costs data centers worldwide are already straining against as AI workloads keep expanding. The researchers themselves noted their design could help alleviate what they specifically called unsustainable energy usage inside data centers, alongside optimizing latency and power consumption, specifically for edge computing scenarios, the kind of AI processing that happens directly on smaller distributed devices rather than inside a massive centralized data center. Think about what solving the interconnect problem, rather than just the raw chip power problem, could eventually mean at industry scale if modest, relatively cheap chips linked with a smart optical network can match or exceed the performance of far more expensive, far more power-hungry GPUs on specific tasks. That reframes the entire cost and energy conversation the AI industry has been having, shifting the conversation away from how do we build an even bigger chip and toward how do we stop wasting so much of the chip power we already have. So here's the full picture, start to finish. GPUs have quietly been losing real performance to a bottleneck called the memory wall, where every layer of an AI calculation has to write results to memory and read them back before the next layer can even begin, leaving processing power sitting idle at every single handoff. A team of researchers at Peking University, led by Xu Haowen and Wang Xingjun, built an entirely optical network to solve that exact problem, replacing copper connections between chips with light-based ones, using a custom 400 gigabit silicon photonic transceiver and a 16 by 16 optical switch capable of scaling to 16 processors and 6.4 terabits of switching bandwidth. Using just 5 modest FPGA chips, running at barely a ninth of a single GPU's rated processing power, that optical connection let the system finish an AI image denoising task nearly 149 times faster than the GPU alone, operating at nearly 95% of its own theoretical peak efficiency, with results verified nearly pixel for pixel identical to the GPU's own output. And critically, the researchers themselves are upfront that this remains a proof of concept, tested on a modest workload with real engineering work still ahead before it could scale to its full 16-chip design or handle the true scale of a commercial AI system. What you're actually looking at here is the same shift that happened decades ago when engineers first realized that copper telephone wires, no matter how much they were improved, would always be outpaced by sending information as pulses of light through fiber optic cable instead. Not a story about one component getting incrementally better, but about an entire category of connection getting fundamentally rethought. Copper wiring built the age of electronics. This research suggests light might be what quietly rebuilds the age of AI. If breakdowns like this, the real research and the real numbers behind China's biggest computing breakthroughs, are useful to you, hit like and subscribe, because there's more of this coming, including a closer look at what happens the first time a system like this actually gets tested against a real, full-scale commercial AI workload, instead of a controlled lab benchmark. So here's the honest question for the comments. Does a result this extreme make you think GPUs are genuinely facing a serious long-term rival? Or does the fact that this was tested on a small, simplified task make you want to see it proven at real scale before you believe the headline number? I read every single one. Inside a lab in Beijing, 5 ordinary chips finish an entire AI task in the time it takes a hummingbird's wing to complete a single beat, while a commercial graphics card working the exact same job is still only a fraction of the way through. That is real. It exists. It's been published in a peer-reviewed journal, and the number attached to it is one that sounds almost too extreme to be true, nearly 149 times faster than the GPU sitting beside it. Every figure in this video comes directly from the published study and specialist science reporting that verified the researchers' own data, because a claim this dramatic deserves real scrutiny, not just a headline. By the end of this video, you'll understand exactly what these researchers actually built, why it beat a GPU by that much, and just as importantly, what it still can't do yet. Here's where this story has to start, because you can't understand why this breakthrough matters without first understanding the exact problem it was built to solve. A bottleneck engineers call the memory wall, and it's been quietly limiting every AI chip on the planet for years. Here's how a typical AI system actually processes information inside a modern graphics processing unit. An AI model, like the ones powering image recognition or language processing, is built from multiple stacked layers. And on a conventional GPU, each individual layer has to finish its calculation, write its results out to memory, and then wait for the next layer to read those results back in before it can even begin its own work. Think about what the back and forth actually costs in practice. Every single layer transition involves a real physical delay, and while one layer is busy writing to memory or waiting on the next layer to catch up, the processor sits there partially idle, burning both time and electricity without doing any useful computation at all. Here's why that inefficiency has mattered so little until recently. For years, the industry's answer to slow AI computation was simply to build bigger, more powerful GPUs and stack more of them together inside ever larger data centers, treating the memory wall as an acceptable cost of doing business rather than a problem worth solving directly. Here's the assumption a team of researchers in Beijing decided to challenge instead. Rather than building a bigger, faster chip to brute force through that bottleneck, what if the actual connection between chips was the thing holding everything back? And what if replacing that connection entirely could unlock dramatically more performance from chips that were never anything special to begin with? Here's the team behind the actual breakthrough. Researchers at Peking University, led by corresponding authors Xu Haowen and Wang Xingjun, published their findings on May 19th in the peer-reviewed journal National Science Review. Here's the mechanism behind what they actually built. And it's a genuinely different approach from almost anything else being tried in the AI hardware race right now. Instead of using copper wiring, the traditional electrical connections that normally shuttle data back and forth between chips inside a data center, the team built an entire optical network specifically designed to link ordinary chips together using light instead of electricity. Here's what ordinary chips actually means in this context, and it's a genuinely surprising design choice. Rather than building custom next-generation AI processors from scratch, the researchers used field programmable gate arrays, commonly known as FPGAs. Reprogrammable chips already widely used across industries ranging from defense guidance systems to autonomous driving, valued specifically for their parallel processing capability, but not typically thought of as cutting-edge AI hardware on their own. Think about what that choice actually signals. This breakthrough isn't fundamentally about inventing a smarter chip. It's about proving that modest, off-the-shelf hardware can dramatically outperform far more powerful equipment, purely by fixing the connection between the chips instead of the chips themselves. The South China Morning Post described the resulting design by comparing it to snapping together Lego blocks, while the trade publication Electronics for You called it an all-optical supernode, built specifically to ease the bandwidth, latency, and energy efficiency bottlenecks that pile up whenever multiple chips have to cooperate on a single AI task together. Here's exactly how the physical hardware behind this system works, because the engineering underneath this breakthrough is genuinely intricate. The team built 2 custom chips to make this optical connection possible. First, a silicon photonic transceiver running at 400 gigabits per second, a component specifically engineered to convert electrical signals into pulses of light, and then convert that light back into electrical signals again on the receiving end. And second, a 16 by 16 non-blocking optical switch, a device responsible for routing that light-based traffic between chips with a total signal loss at or below 5 decibels, low enough, according to the published research, to move data essentially error-free without needing additional optical amplification along the way. Here's the detail that shows this system was built with genuine room to grow rather than as a one-off lab trick. By packing 4 separate wavelengths of light onto a single fiber optic strand simultaneously, the switch lets each individual chip occupy just one physical port on the network, meaning the same underlying architecture can scale up to 16 total processors working together, supporting a combined switching bandwidth of 6.4 terabits per second. Here's what the researchers actually did with 5 of these chips connected together for their initial demonstration. They linked 5 FPGAs through this custom optical switch, with each individual chip assigned to handle exactly 1 layer of a 5-layer neural network, specifically designed to strip visual noise out of images pulled from the Fashion MNIST dataset, a standard benchmark set of clothing images commonly used to test image processing AI systems. Here's the number that anchors this entire story, and it's worth sitting with the full comparison rather than just the headline multiplier. The 5-chip optical system processed 1,000 images, each containing 32,768 bits of data, completing the entire task in 105.16 microseconds, a unit of time so small that a single blink of a human eye lasts roughly 3,000 times longer. Here's the benchmark the researchers measured that result against. A commercially available graphics card rated at 16.96 teraflops of processing power took 15.6 milliseconds to complete the exact same task using the exact same images. Think about what those 2 numbers actually mean side by side. The optical FPGA system finished in a fraction of a millisecond, what took the GPU over 15 full milliseconds, working out to the study's headline figure of nearly 149 times faster completion. Here's the detail that makes this result genuinely credible, rather than just a flashy number pulled out of context. The researchers didn't just report a speed figure and move on, they also ran the identical images through the GPU separately and directly compared the 2 systems' outputs pixel by pixel, confirming the results were nearly identical, meaning the optical link wasn't cutting corners or sacrificing accuracy anywhere along the way to hit that speed number. Here's the number that makes this result even more remarkable, once you actually think it through. The 5 FPGAs combined delivered only about 1.969 teraflops of raw computing power, roughly 11.6% of the GPU's own rated capacity, meaning the system didn't win by being more powerful hardware. It won using barely a ninth of the GPU's own processing muscle, purely by fixing how those chips talk to each other. Here's the mechanism that actually explains why removing the memory wall produced a result this dramatic. On a traditional GPU running a multi-layer neural network, remember, each layer has to write its results to memory and then read them back before the next layer can begin, with every layer sitting there waiting on the one before it, and processing capacity going idle during every single one of those handoffs. Here's what the optical link does completely differently. Instead of writing results to memory and reading them back, data passes directly from one FPGA to the next across the light-based connection, moving from layer to layer, the way parts move down a physical assembly line, each station immediately ready to work the instant the previous one finishes, without ever putting anything down and picking it back up again. Here's the number that proves this design actually delivered on that assembly line promise, rather than just sounding good on paper. The 5-chip system operated at 94.7% of its own theoretical peak performance, an extraordinarily high real-world efficiency figure for any computing system, let alone one built from repurposed, off-the-shelf hardware rather than custom silicon designed from scratch for this exact purpose. Think about what a 94.7% efficiency figure actually represents. It means almost none of the system's theoretical capability was being lost to overhead, idle waiting, or wasted cycles. Nearly every bit of computing power these modest chips had available was actually being put to productive use, moment to moment, across the entire task.